Hello everyone. In the second topic, we need to use the settling time and steady state to identification process. The system identification, for to what it's based on the settling time and steady state values for first order system. We may have the different methods to do that. Okay, this is our topic. So the objective of this notes, the application notes, the building mathematical from measured data. Okay, and also the creating to what discrete model to define real parameters. It's the system. Okay, for example, the J and C, right? Because if you don't have the discrete model, we cannot model it, because it's everything that's coming from the measured data is in the form of the discrete. Okay, and so after that, the using the first order dynamics or the time response params, for example the tau or steady state error, to model the R system. Okay, so in the first place we should write the system model again. We need to convert the whole dynamics into the coefficients, just like this one. The DC motor model is given by with the J W dot plus C W is equals to the K V U T. Just remember the previous form. This is the PWM. It's coming from your discrete model. This is the coefficients, motor coef, to convert this kV times ut into the torque values, because we can only apply the torque value to this form. Just remember, this is the angular speed, and also the other J and C. J is inertia, C is the damping or damper coefficients. Okay, and so we need to write to this form into the Laplace transformation. 1.2 Laplace transformation should be applied on this equation, and also we need to obtain the transfer function. Okay, so in the Laplace domain with zero initial conditions, we have the Js Ws plus C times Ws is equals to the Kv times Us, and so we can write the Gs as equals to the Kv divided by Js plus C. Just reorganize the equation in terms of the Wc divided by Uc, right? This is equals to the transfer function of these terms, and so we can write the form as just like this one. Gs is equals to the Kv divided by j s plus c divided by j. Just remember the transfer function form. The roots of the denominator or the characteristic equation is equals to what? The tau value. Okay? And so we can write to what, or we can continue with the what? The time domain response. Time domain response. Okay? These are the conditions. First of all, if you are applying the 100 PWM rate in here, we should assign to what? The unit step signal, because it does not change through the time, going to the what? The infinity values. Okay? And so the for unit step signal, we can assign the ut is the what? The u0, which is assigned to the 100 or 6 or 50 or 40. Okay? And so in the transfer function domain, we have to what? The us is equals to what? The u0 divided by s. Okay? In the Laplace domain. And so ws, which is equals to the what? The us times gs. And so we have the kv divided by j s plus c divided by j times u0 divided by s. Okay? And so in time domain, if we solve this equation, and then we will have to what? To this one. Wt is equals to the what? kv times u0 divided by c times 1 minus exponential over c divided by j times t. Okay? And so this c divided by j is going to the what? This value. The inverse values of these terms is equals to the what? Is equals to the time constant. And so the steady state gain, this is the steady state gain, because the t is approaching to what? Infinity value. These terms removes 0, and always we will have the kv times u0 divided by c. And also this is equals to the what? The frequency constant, or the time constant in here is equals to the what? Is equals to the j divided by c. Okay? Because in the basic representation, this equals to t divided by tau in normal condition. And so steady state value is equals to this one. The time constant is this one. Okay? And after that, we should write to the what? The key characteristics coming from this equation. See, first of all, the steady state value is equals to the what? WSS is equals to the kV times U0 divided by C. This is the first equation. And so the time constant is also another important parameter. Time constant is equals to the what? The time at 63.2% of steady state value. Which means that if we analyze the RWSS at the end of the what, t is going to the infinity values, and so this value multiplied with the what? The 0.63, and so this values is the what? Is, for example, the WSS. SS times 0.63. Okay? And so we search the whole the graph just like this one. This is the VSS, and so for example this is the 0.6 VSS, and then we need to find this value, time tau. And so we can easily determine to the what? To this value from these settings. And after that, we should also utilize the settling time in here. Okay, the settling time is the time at remain error between the RWT is going to what the WSS, or the disk GC gain, which is symbolized with the delta of steady state value. Okay, and so our basic equation can be given with what, for first order TS is equals to what, minus tau value, which is coming from the J divided by C times Ln delta. Okay, and so we can easily assign the delta is equals to the what, the minus plus 2%, or for your implementation for a noisy signals, we can assign the 5% of this value. For example, if we choose the what, the delta is equals to 0.02, and so this TS is equals to what, the tau times Ln 0.02, which is equals to what, the 4 tau value. Okay, and so the settling time is direct representation of the what, the 4 times tau, and so the tau is equals to what, the J divided by C, and so we can easily find the what, our tau value based on the what, the settling time. And so this could be the error rate of the what, the 2% error at the end of this graph, and so we can assign these values easily. We can identify the system parameters. And so how we can do that? Continue with the what, the 1.4 parameter estimation using time domain keys. This is our topic. And so first of all, the estimating time constant. How we can do that? The estimated time constant based on what, the TS settling time, the tau estimated is equals to what, the minus TS Ln delta value. Okay, and so the delta 0.05, a 5% error can permit to what, to find the TS value in here. For example, if you put this delta value into the what, Ln form, and so the tau estimated value is closing to what, the TS and 3. Okay, and so this is obtained from the what, from the graph or measured data. Okay, so in the second case, estimating steady state gain. KV divided by C. U0 is the external input, and so we don't need to find this U0 because we know already U0. Okay, and so the from the what, WSS, which is coming from the what, the graph, and so KV times U0 C. U0 is known, WSS is known from the graph, and so the KVC divided by C is equals to what, WSS U0. Okay, and so these two parameters are found right now because the tau estimate is also J divided by C. And so just remember to the what, to the our physical parameters. I'm writing just like this one, WS divided by US is equals to the what, KV divided by J, and S plus C divided by J. And we already know the J divided by C, tau value, and K divided by C. Okay, and then we should calculate J in here from the mechanical parameters, and then C estimation value is equals to what, to J divided by tau est. Right? This is the first parameter. And also the k v est is coming from this equation is equalized to the what? The c est times w ss divided by u0. This is the second parameters. Okay? And after that, the whole equations can build with the what, or the transfer function can be written as gs is equals to the what kv est divided by j s plus c est divided by j. Our basic equation is given from to what, to these terms. Okay, so these are the basic theory, but right now we need to consider the practical implementation. We should build a systematic solution for these representations. First of all, the step 1. Just remember the previous lesson. We have talked about the low pass filter. To what? To our signal, to remove the noises from the measured signals. Okay? And so the measured signals, noisy signals, is performed with the what? With this one. In the discrete domain, W filtered K can be defined with the what? The alpha, which is the constant, times W noisy K. Right? These are the signal. This is the measured signal coming from the what? It's the RDC motor, and 1 minus alpha times W filtered K minus 1. This is the simple representation of the what? The low pass filter in the discrete domain. And so the alpha can be assigned with the what? The 2.pi.fcts divided by 1 plus 2 pi fc times ts. In here, fc cutoff frequency to filter the R signal. The ts is the sampling rate. Just remember that we cannot directly use the what? The continuous method, because we have everything in the form of the discrete domain, not the other one, guys. Just remember, but this alpha is computed with a discrete low pass filter based on the what? Based on the applying to the noise filter, noisy signals. And so if we calculate this alpha value, we can set the what? To the cutoff frequency and sampling period, and we will get to the what? The correct values of the discrete low pass filter. This is important. We cannot use the continuous formation here. Just remember that. And so if we obtain the whole the measure signal, and after that we apply the low pass filter. After that, in the second step, we need to estimate steady state value. Okay? And so how we can do that? We need to compute average values of filtered response over the last 10% of data, measured data. For example, if we have the 5,000 data measured from the DC motor in real-time application, and so we will get the what? The 500 values, but the last 500 values indicate the steady state values. This is the correct formulation to what? To contain these values. And so how we can model it? And SS is equals to what? The 0.n, and the total sampled number. Okay, so WSS can be built with what 1 divided by this, the average value n minus nss, the total number sample period, the nss, which is equals to what 0.1 n plus 1 times the average value can be found with the index of k and ss to what to n, and w filtered value k is assigned, and so the r steady state value from the what from the graph can be built, can be calculated based on these parameters. Okay, and after that we find the steady state values, but we need to determine also settling time, right? TS. So in order to do that, it's applied on the graph, we need to build the band with the what w upper can be defined with the last value vss 1 plus tau, right? Not tau, this is the delta value 0.05. Okay, and also the lower bound is assigned to the what the wss times 1 minus delta. Okay, and so how we can define this ts value, assign ts at the what t first value such that we filtered k is found in the what in the subset of the v lower value w upper value. If what if we search the whole the filtered data, and so if we looking for the w lower and w upper, and so if our filtered k is in the what between the w lower and w upper value, we should assign ts at that point at the first time. Okay, this is how we can determine to the what the settling time for a given graph or the measured data. Okay, this is step 3. And after that we need to continue with the what the step 4. In the step 4 we need to estimate the time constant tau est. If you know the what the settling time tau est, ts divided by 3 should be assigned for, but delta is equals to the 5%. Okay, this is the 5%. And also step 5 and estimate damping or damper coefficients in here C est, and so the calculated j known in here, and so the C est is assigned to the what the j divided by tau est. Okay, these are the formulations. Tau s and tau s is utilized to what to find this value. And after that in the step 6 we should estimate motor constant kV, right? And so using the what the steady state error kV est can be calculated with the what the CS, which is already known in here, calculated, and WSS is obtained and U0 known, and so we can calculate these values. After that in the step 7 use MATLAB or in MATLAB validate responses based on the what comparison of real or measured and the estimated time response. Okay, so In the next lesson, we will write this code on the MATLAB platform. Okay?